Hi, I'm Chase Dwelle, the founder of Fix6, and we're measuring the world's carbon to connect more people to the carbon economy. People like Musa, who wants to develop a larger scale agroforestry project in Tanzania, but like a lot of project developers and land stewards we're seeing, he wants to start small so he can flex his regenerative agriculture muscles before really diving into a large scale project. And for people like Musa and other small landholders or project developers, Fix6 is focused on developing a scalable and flexible MRV solution that can grow with the climate ambitions of our project developers. And one of the reasons we're focused on scalability is historically smaller landholders and product developers have been blocked from the carbon economy, in part due to MRV costs that lead to these monstrous project sizes. On the other hand, the median project size for Fix6 for 11 pilot projects is just 115 acres compared to the 30,000 plus acre projects we see on registries like Vera. And this is important because we see almost all farms over the world are smaller than 125 acres, and half of global farmland is on farms smaller than 500 acres. So having an MRV solution that works for these smaller landholders opens up an entirely new group of customers that can benefit from regenerative agriculture on their lands. And the process that we use for our MRV really fall into four different buckets. So of course we start with data. So we collect geospatial information as well as weather, climate, soils, and vegetation data for our project, along with remote sensing data. And we use all this to train our physics-informed machine learning model. So we'll get into that a little bit later, but this allows us to simulate project sequestration as well as provide sequestration forecasts. And this all comes from this physics-informed machine learning, where we can use both remote sensing and also ground truth data to train our physics engine. And also importantly, because a lot of these projects span the course of decades, we provide risk models for these projects. So for instance, changing precipitation or climate patterns could have an impact on the health of vegetation over the long term. So we are developing risk models for this, as well as providing product monitoring and updating medium-term forecasts over time for each of these projects. And this is all in the benefit of scaling. So we are integrating with marketplaces and DMRV protocols to get this data information out into the world, and also focusing on our Carbon API so we can get more customers this information. So if you're interested in the Carbon API, feel free to get in touch. I'll go over it briefly here in a second. So our Carbon API is really focused around the geospatial information of the project. So if you have a GeoJSON or shapefile associated with the project, you can upload that or post it to our API. And that kicks off a whole series of processes on the back end, which allow you access to data about that project, be it historical weather data, climate data, important information like a wetlands masks. So this can be important because some methodologies don't allow you to perform a project on wetlands. So that can be important. We also give you access to the remote sensing data through indices, or through remote sensing indices for that project. Also information about the soils on the site. But what most people are interested in is the actual carbon data. So we generate 3 or 4 different things here. One is the carbon baseline. So this is the carbon sequestration over time. This is a time series. Over time of what would happen under the baseline scenario, so under current practice and vegetation type. And we also work with you to understand, what new practice is being put in place, and so we provide sequestration time series under that new practice, as well as carbon emissions, greenhouse gas emissions for that project. And this all allows us to construct an additionality time series, which is essentially the difference between those last 3 time series, so you can get an understanding of the crediting available for that project. And we're doing this so we can get all this data information that we provide out into the world. So we're interested in having a lot of transparency around data, processes, and also outputs of our MRV protocol. So if you're interested in the API, get in touch with us. I'll give my contact info at the end. We've gotten a lot of questions about how this physics-informed machine learning works. We'll be releasing a series of articles over the summer, kind of diving into this in detail. But just briefly, I'll go over the physics generator that we use, or the physics engine that we use. So essentially, we explicitly model the energy, water, and carbon cycles on the project area. So we'll do this in the case of a tree or a forest here, but this works with any type of vegetation. Essentially, you have energy coming into the project through essentially the sun. That energy gets used by the plant in order to drive photosynthesis, but that is also coupled with the water and energy cycles. And so from the water cycle, we get rain or irrigation coming into the project area that essentially goes into the soil, which makes the water available for root water uptake to drive photosynthesis. And that's really the driver of our carbon cycle. So there's a lot of processes in here, but one thing that I want to focus on is the carbon allocation piece. So we get essentially the net productivity of that, but we are able to allocate it into different parts of the plant depending on characteristics of the plant. So for a tree, in instance, we can allocate carbon to the leaves, stems, roots, and trunk of that tree, and also fruit and flowers if it's an agroforestry project. And that's important so we can, allocate, above and below ground biomass so we can see kind of what's going on throughout the entire tree, and instead of just looking at essentially what's going on at the canopy or top of the vegetation labeled through remote sensing. We combine all this together because there are pretty complex interactions between each one of these cycles, so explicitly modeling each of them out helps us understand better the carbon sequestration of a given project, of the given vegetation in that project. If you're interested in anything I went over, be it the Carbon API or the process we use for physics-informed machine learning, feel free to reach out. Or if you're interested in collaborating or getting access to our data, potentially for a protocol or for your own projects, feel free to reach out. My email is here, chase@fix6.io. Thank you.